Hello, my name is Shahriar Shahriari, and this is a lecture in a series of lectures on high school mathematics. The topic of this lecture is exponents, very basic definitions, rules, and examples. In this lecture, to tell you about the notation and meaning of exponents when the exponent is an integer, things like 2 cubed, 2 to the minus 5, 2 to the 0, what it means and how you deal with them. In the next video, we will talk about rational exponents, where the exponent is a ratio of two integers, things like 2/3 or 5/7 and so forth. If we want the exponents to be irrational, things like square root of 2 or pi or e, then actually for that you need limits or calculus. You need a little bit fancier machinery to be able to understand what those things mean. We will also talk about the algebraic rules for exponent. We will briefly talk about exponential functions, things like 3 to the x and 3 to the minus x. And as an example, we look at compound interest. 2 times 2 times 2 times 2 is 16. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Our shorthand for that is 2 to the 4th equals 16. We write a 2 with 4 as a superscript. This is just notation, and we read it as 2 to the 4th power is 16. We also say if you raise 2 to the 4th power, you get 16. But all we're saying is that 2 times 2 times 2 times 2, 4 of them, equals 16. 2 is the base, and 4 is the exponent. This is just notation. This particular notation goes back to René Descartes from 17th century, but working with exponents and trying various kinds of notation for it started back in the medieval times in the Islamic world. But over time, different notations were tried, and the one that stuck was Descartes from the 17th century. So what's minus 3 to the 2? It just means minus 3 times minus 3, and that's 9. But minus 3 cubed, on the other hand, is minus 3 times minus 3 times minus 3, and that's minus 27. What's apple to the 3? Well, it's apple times apple times apple. What's y to the 4th is y times y times y times y, if y is an unknown. And what's 2/3 cubed is 2/3 times 2/3 times 2/3. When you have fractions and you multiply them, you just multiply the numerator straight up and the denominator straight up. The numerator is 2 times 2 times 2 is 8. 3 times 3 times 3 for the denominators is 27. So you get 8 over 27. What's 0 to the 5th? Well, that's just 0 times 0 times 0 times 5 times, and that's a 0. In fact, 0 to anything other than 0 is 0. So our definition is that if n is a positive integer, then a to the n means you take a and multiply it by itself n times. What if n, that exponent, is not a positive whole number? If it's 0, then we define that a to the 0 to be 1. This is not something we can prove. We're just deciding that a to the 0 equals 1. But this is only as long as a itself is not 0. If a is 0, then we have 0 to 0, and that we cannot define. What's 5 to the 0 is 1. 1/3 to the 0 is 1. Minus 47 to the 0 is 1. Square root of 3 to the 0 is 1. Apple to the 0 is 1. Well, as long as apple is not 0. If you don't know what apple is and it could be 0, you've got to say that apple is not 0. Move on to negative powers. This is something that students a lot of times get confused by, but if you have anything to a negative power, then all you do is you write 1 over that same thing, but to the positive power. So apple to the minus n does not mean minus something. It's not a negative number. It's 1 over apple to the n. This is as long as apple is not 0, because if apple is 0, then you're dividing by 0, and that's a no-no. You can't divide by 0. So for example, what does 5 to the minus 3 mean? Well, it's not a negative number. What it is 1 over 5 to the 3rd power, and 5 to the 3rd power is 5 times 5 times 5 is 125. What's x to the minus 4? If x is some unknown mystery number, it's 1 over x to the 4th, but as long as x is not 0. And what's 4/7 to the minus 2? It's going to be 1 over 4/7 squared. And what's 4/7 squared? It's 4/7 times 4/7, and that's 16/49. And what's 1 divided by a fraction? Well, you flip the fraction over and you get 49 over 16. And you might notice that 49 over 16 is actually 7 over 4 squared. So when you have a fraction to a negative power, basically what you do is you flip the fraction, but make the power positive. Now, here's some exponent rules. There's 3 rules basically that you have to know. The first rule is that if you're multiplying 2 exponents and the bases are the same, you add the exponents. So apple to the a times apple to the b, because the bases are the same, it's apple to a plus b. And apple to the a to the b. If you take an exponential and then find the exponent of that, you multiply. Apple to the a to the b is apple to the ab. And apple times strawberry multiplied and then raised to the power a is the same as apple to the a strawberry strawberry to the a. These are rules that do need actually proof. The proofs are not that complicated, but I'm not going to spend the time here to go through them. Basically, the proof of the pudding is in the eating. You just see what each component means. But how do you remember these? And in fact, what I'm going to tell you is basically how the proof also goes. If you forget, all you do is try a simple example, and that will jog your memory. For example, to remember the first rule, apple to the a, apple to the b, when the bases are the same, what happens? Well, just try something like 2 cubed times 2 to the fourth. In math, when we are multiplying things, sometimes we don't put the times sign, but that still means times. So 2 cubed times 2 to the fourth. What is that? Well, 2 cubed is 2 times 2 times 2. That's what 2 cubed means. And then we're multiplying that by 2 to the fourth. But what's 2 to the fourth? Well, that's 2 times 2 times 2 times 2, 4 twos. So now we're multiplying all these twos together. How many twos are we multiplying? We're multiplying 7 twos. So that's 2 to the 7th. This should remind you why apple to the a times apple to the b is apple to the a plus b. Basically, apple to the a means you're multiplying a apples. Apple to the b means you're multiplying b apples. And then together, that's a plus b apples. That proof only works if a and b are positive integers. So you have to also do the case where one of those is negative, but that basically brings something in the denominator and things get canceled and works just as well. How would you remember the second rule? Apple to the a to the b is apple to the ab. Just try a simple example. What's 5 cubed squared? 5 cubed squared means 5 cubed times 5 cubed. Apple cubed is apple times apple times apple. So 5 cubed is just 5 times 5 times 5. And the second 5 cubed is also 5 times 5 times 5. And so I have 6 5s because I have 2 sets of 3, and that's 2 times 3 is 6. So I get 5 to the 6. It's always in math better to go to first principles than try to memorize a whole bunch of stuff. Things you memorize, you forget, but if you make an argument, you will remember. And here what I'm telling you is just look at a simple example. For that last one, I might not remember apple times strawberry to the a power. What is that? Well, I'll try something. 3 times 5 squared. Anything squared is that thing times itself. So I have 3 times 5 times 3 times 5. So you can multiply the 3's together, then the 5's together, then multiply the result. And so you get 3 squared times 5 squared. And you see that that exponent 2 became the exponent for 3 and 5, just like the rule. So again, if you don't remember these rules, not much is lost. All you do is try a simple example. The rules that we just saw was that x to the a times x to the b is x to the a plus b, x to the a to the b is x to the ab, and xy to the a is x to the ay to the a. I said that x and y should be non-zero, and a and b can be any integers. X and y should be non-zero. If one of those exponents is a negative exponent and then x is 0, then you might get a 0 in the denominator, and that's the problem. You actually don't need to know any other rules, but there are other rules you can get from them. For example, we said x to the a times x to the b is x to the a plus b, and you might ask, well, what about x to the a divided by x to the b? The point is that x to the a divided by x to the b is the same as x to the a times 1 over x to the b. So what? Well, 1 over x to the b is the same as x to the minus b. Now we have a product with bases the same, so we can use our rules and add the exponents. And a plus minus b is a minus b. You can think of this as a new rule if you like. X to the a divided by x to the b is x to the a minus b, but this follows from the other ones. This rule does give us a reason why we said 5 to the 0 or 2 to the 0 is 1. First of all, you believe me if I say 8 divided by 8 is 1, and that's the same as saying 2 cubed divided by 2 cubed is 1. No mystery there, nothing up my sleeves. But 2 cubed over 2 cubed, according to this rule we just found, should be 2 raised to the power 3 minus 3. The bases are the same. You should subtract the exponent when you're dividing. But 3 minus 3 is 0, and you get 2 to the 0. So 2 over 2 cubed is 1, but it's also 2 to the 0. So that tells us that if we want 2 to the 0 to mean anything, it should mean 1. The thing that needs proof is x to the a times x to the b is x to the a plus b. If I had not defined something to the 0 to be 1, then this rule would work, but not in all cases. If I want these rules to work for everything, then the thing to do is to define something to the 0 to be 1. One final rule, we had said that xy to the a is x to the a, y to the a. What about x over y to the a? Notice that x over y is the same as x times 1 over y. 1 over y is y to the minus 1. And now we can use the rule apple times strawberry to the a is apple to the a, strawberry to the a. And so we get x to the a, y to the minus a, but y to the minus a is 1 over y to the a. You could think of as another rule. X over y to the a is x to the a over y to the a. I'm going to summarize, and this is basically all you need to know about exponents. If n is a positive integer, then a to the n means a times a times a n times. I've said this before. I'm just repeating myself. A to the 0 is 1 as long as a is not 0. 0 to 0 is not defined. A to the minus n is 1 over a to the n. N is a positive integer, so minus n is negative. And if you take a to that, you get 1 over a to the n. That's as long as a is not 0, because if a is 0, then you get a 0 in the denominator. you don't want that. Those are the definitions, and the rules are that for non-zero numbers and for integer exponents, x to the a times x to the b, when the bases are the same, you add the exponent. So you get x to the a plus b, x to the a to the b, one exponential, and then raised to another power, you multiply a and b, and xy to the a is x to the a, y to the a. We had these two other ones, x to the a over x to the b is x to the a minus b, and x over y to a is x to the a over y to the a. But my point is that if you just know the basic definitions, the ones in blue on top, if you know these definitions, then by trying one simple example, you will discover what these rules are. You don't really have to memorize them. But after a while, they become second nature, and that's helpful when you want to do things quickly. Let's look at some examples. 54 times 1/12 the second times 3 to the minus 1 divided by 36. Can we simplify that or not? I'm going to pre-process things, and I'm going to factor things. So 54 is 2 times 27. 27 is 3 cubed. So 54 is 2 times 3 cubed. 12 is 2 squared times 3, and 36 is 2 squared times 3 squared. I see that 1/12 squared, and I don't like that. I'm going to simplify that. 1/12 squared, that x over y to the a, it's 1 squared, 12 squared. 1 squared is just 1. 1 over 12 squared is 12 to the minus 2. And 12, we said that was 2 squared times 3. So we have 2 squared times 3 raised to the minus 2. It's xy to the a is x to the a, y to the a. So it's 2 squared to the minus 2 times 3 to the minus 2. And 2 squared to the minus 2 is 2 to the minus 4 because you multiply 2 and minus 2. So you get 2 to the minus 4 times 3 to the minus 2. A lot of this you could do in your head when you get good at it. Now let's go back to the original problem. So instead of 54, I'm going to put 2 times 3 cubed. Instead of 1/12 squared, I just find out that that's 2 to the minus 4 times 3 to the minus 2. 3 to the minus 1, I just keep. And instead of 36, I'm putting 2 squared times 3 squared. On top, I see that I have a whole bunch of 2's. 2 times 2 to the minus 4. That's going to be 2 to the minus 3 because the bases are the same. You add the exponents. 1 minus 4 is minus 3. What about the 3's? The 3 cubed times 3 minus 2 times 3 to the minus 1. There's 3 things with 3 as a base. I can just add the exponents. 3 to 3 minus 2 minus 1, and that's 3 to the 0. And the denominator I just kept. Now, what's 3 to the 0? That's just 1. So I just have 2 to the minus third over 2 squared times 3 squared. But what's 2 to the minus cubed? That's 1 over 2 cubed. So I have 1 over 2 cubed times 1 over 2 squared times 3 squared. I can combine them. I get 1 over 2 to the 5th times 3 squared. 2 to the 5th is 32. 3 squared is 9. And that's 1 over 288. There's many other ways of doing it. Like, for example, right off bat, you could have noticed that 36 and 54 have a factor of 18 in common, and you could simplify those. And so then this would have become 2, and that would have become a 3 instead of 54. Here's another example. Earth's mass is approximately 6 times 10 to the 24 kilograms. 10 to the 24 means 10 times 10 times 10, 24 times. So 1 and then 24 zeros. That's a lot because you multiply 6 by that, you get 6 and then 24 zeros. But sun's mass is actually a lot more. It's 2 times 10 to the 30 kilograms. My question for you is the mass of how many Earths is equals to that of the sun. So if someone was going to pick up the sun, that's equivalent to picking up how many Earths. If you want to see how many of this fit into that, you divide. We take the mass of the sun and divide it by the mass of the Earth to see how many Earths are equivalent to one sun. This is the same as 2/6 times 10 to the 30th divided by 10 to the 24th. 2 over 6, that's 1/3. What about the other thing? Bases are the same, and we're dividing. We'd subtract the exponent. So that's 1/3 times 10 to the 6th. 10 to the 6th is a million, approximately 333,000. 1/3 is 0.333333. If you multiply it by a million, you get 3333333. But I didn't write it like that because everything here is approximate. If I wrote it as 333,333, you would be under the impression that I'm giving you something more precise than I really can. My data is not precise enough for me to say that. It's more prudent to round and say approximately 333,000 Earths weigh the same as the sun. Let's talk about exponential growth and decay for a second. This is a little story that goes back many, many centuries. It's a story about the inventor of chess. The versions of this story that we have come from the Iranian plateau and the Islamicate world in the medieval times. Chess was purportedly invented in India and then made it to Sassanid Iran, where it was called Shatranj and was played quite a bit. The story goes, and this is just a myth, that the king who met the guy who invented chess was very happy with the game and asked the guy to name his prize. And what he said is that, I don't want much. Just give me 1 grain of wheat on the first square and then double that on the next square. So in the next square, give me 2, and the next one, give me 4, and then give me 8. And just do that on the chessboard on the whole thing. And that's all I want. And the king said, oh, that's ridiculous. I asked you to tell me whatever prize you want, and this is all you want? So he wanted 1 grain, that's 2 to the 0 in the first square. And then the next one, twice that. So that's 2 to the 1, then 2 squared, 2 times that, and then 2 cubed all the way to 263. The point is that exponents like this grow really fast. And 2 to the 63, that last square, is this many grains of wheat. And actually, the guy had asked for the sum of these. And so how much is that? How do you find this? This is a partial sum of a geometric series. Every term in these things we're adding is twice the previous one. And for that reason, I'm going to multiply s by 2. If I multiply by 2, 2 times 2 to the 0, that's 2 to the 1. 2 to the 1 times 2 to the 1, that's 2 squared, all the way till 2 to the 64. So twice s is 2 to the 1 plus 2 squared, all the way 2 to the 64. Let's subtract these, 2s minus s. So if you have 2 apples and you eat one of them, you're left with 1. So 2s minus s definitely is s. But you could also subtract the right-hand sides. And if you subtract the right-hand sides, many things cancel. In fact, this 2 to the 1 cancels with that 2 to the 1, 2s minus s. 2 squared cancels with the 2 squared there. And the 2 to the 63 cancels with the 2 to the 63 down here. So the only thing that are left are the 2 to the 64 and 2 to the 0, which was 1. So you get s is 2 to the 64 minus 1. And 2 to the 64 minus 1 is this humongous number. It's 18 quintillion and change. So this is the amount of grain that this fellow was asking. And actually interesting that on that last square, he's getting more grain than the whole of the rest of the chessboard combined. We can also graph this. On the x-axis, we put n, and on the axis, we put powers of 2. When n is 0, 2 to the n is 1. When n is 1, I get 2. When n is 2, I get 4. When n is 3, I get 8. When n is 4, I get 16. And as you see, these things are going up quite fast. I could go the other direction as well. I could put n equals minus 1, and then I would get 1/2. And if I put n equals minus 2, I get 1/4. And this is what an exponential growth looks like. And you could connect these and you would get this exponential growth function. And this is 2 to the n, 47 to the n would be even steeper than that. It might look like this curve is going to 0. It's not, but it's just getting really close. And so my graph doesn't show it. The n-axis is an asymptote way back down there. However, to draw this graph the way I did it and not as dots, if you connect them, then you're making the assumption that even when n is not integer, the 2 to the n means something. In the next video, we'll talk about if n is 1/2 or 1/4 or 1/5 or 3/4 and 3/8 was 2 to the n means. But it also means things when n is any real number. That's a more complicated story. Instead of 2 to the n, look at 2 to the negative n. And in that case, we will see what's called an exponential decay. For example, if n is 2, we get 2 to the minus 2, which is 1/4. But if n is minus 2, then we get 2 to the minus 2, 2 squared, which is 4. The only point I'm trying to make is that exponential functions grow fast. As one final application, we'll look at compound interest. Put $1,000 in an account with 7% annual interest rate, compounded monthly. So what does that mean? After the end of the month, they will say that, okay, we'll give you the interest. And then the next month, they will give you an interest, not just on your principal, the amount you put in the bank, but also on the interest that you got previous month. And that means that's compounded monthly. My question is that how much would be the total money that you have after 120 months? So $1,000 account, let it sit for 120 months, and you're getting 7 annual interest compounded monthly. Let's think about that 7% annual interest. What does that mean? Well, that means that every month you are getting 7/12%, and that's 0.583% interest per month. And that's percent. So 0.583% means 0.583 divided by 100. So that means 0.00583 is your interest per month in decimals. What that means is that if you have $1 for 1 month, then you get $0.00583 in interest. That's not that much. It's not even a cent. It's like a half a cent in interest. If you have Apple dollars for 1 month, you get 0.00583 times Apple dollars in interest. So if you have $1, you get 0.00583. If you have $2, you get twice that much. If you have $3, you get 3 that much. If you have Apple dollars, you get Apple times that number, 0.00583 dollars in interest. But you have also your principal. After 1 month, the principal plus interest, the original money you put in plus the interest, will be Apple. That's how much you put in. And then 0.00583 apples. If you factor an Apple after 1 month, in total, you'll have Apple times 1 plus 0.00583. So keep that idea that if you have Apple dollars after 1 month, you multiply it by 1 plus 0.00583. And what's 0.00583? That's the interest rate per month in decimals. The problem was that we have $1,000, 7% annual interest compounded monthly. What happens after 120 months? If you have Apple dollars, that becomes Apple times 1 plus 0.00583 after 1 month. So after 1 month, if I start with 1,000, it would be 1,000 times 1.00583. But what about after 2 months? Now, in the second month, I don't start with 1,000. I start 1,000 times 1 plus 0.00583. That's how much I started the month with. But then I multiply it by another 1 plus 0.00583 to see what happens at the end of the month. And because the bases are the same, you're adding the exponents, which are both 1, and you get 1,000 times 1 plus 0.00583 squared. After 3 months, again, you multiply that by another 1 plus 0.00583, so that becomes to the third power. And this continues, and after 120 months, you will have 1,000 times 1 plus 0.00583 to 120, which is approximately $2,008.86. More generally, if R is the interest rate per compounding period in decimals, R is not the annual interest rate. If your interest is being compounded daily, you have to find out what the interest is per day, and that would be the annual interest divided by 365. You don't want it in percentage, you want it in decimals. If N is the number of periods, the number of those compounding periods that you keep your money, and P is the principal amount, then the future value of the investment is P, that principal, times 1 plus R to the N. And this is the end of this lecture about exponents. The next lecture will be rational exponents and radicals, and the one after that will be about logarithms. Till next time.